So, dear students, welcome to another lecture of basic electrical engineering. In this particular lecture, we will discuss about the principle of operation of a three-phase induction motor. So, this lecture is purely dedicated to the concept of the working principle of a three-phase induction motor. Now, in our previous lecture, we have already discussed that a three-phase induction motor is a self-starting motor. Now, why it is self-starting, that also we have discussed. Now, it is self-starting because we have a rotating magnetic field. So, for example, this is a stator and this is the rotor. The stator as well as rotor of a three-phase induction motor has three-phase winding. For example, the windings are in star connection or delta connection. There can be any kind of connection, whether star or delta. In case of the stator or rotor winding, generally stator winding is connected in star or delta. The rotor construction is of two type. One is we have the cage type of rotor, then we have a wound rotor formation, right? So now when we provide supply to the stator, right, when we give a three-phase AC supply to the stator winding of a three-phase induction motor, what happens in the air gap, right? So we have the air gap, let us say this is the air gap. So in this air gap we have the rotating flux, right? Or we have the flux which has the rotating nature, so which is rotating in a clockwise direction with a certain speed, and this speed is given by an s is equal to 120 f by p. So where f is the frequency of the input supply, right, and p are the number of poles of the motor. So that means the speed at which, so this is the speed of rotating flux, and this speed is known as synchronous speed. So synchronous speed is that speed at which the flux rotates in a three-phase induction motor. Now, what happens, like we have a cage type rotor, for example. So in a cage type rotor, we have the conductor bars placed on the rotor periphery, and these conductors are connected, shorted, basically they are shorted to one another using the end rings. So end rings are used to short these conductors back to back. So when we have a rotating flux in the air gap, and this flux, because it is rotating in nature, so what happens, this flux cuts the conductors, and as per Faraday's law of electromagnetic induction, we have an EMF induced on these conductors, which is given by E is equal to minus d phi by dt. Right. Now, this seems to be the principle of, or this seems to be the transformer action. Like in transformer, we have a primary winding and we have a secondary winding. So the supply is given to the primary winding, and the output is taken from the secondary winding of the transformer. Now assume here that the stator winding is the primary winding of the transformer and rotor's winding is the secondary winding of the transformer. So when we give supply to the motor's primary winding, that is to the stator of the motor, it generates a rotating flux. So this rotating flux cuts the conductor which are placed on the rotor. Now when we have an interaction of the conductor and the magnetic field, so as per Faraday's law of electromagnetic induction, these conductors will have an EMF induced over them, which is given by E is equal to minus d phi by dt. Right. So the same thing happens in the transformer also. So we give an AC supply to the transformer's primary, and because of this AC supply we have uh, a bidirectional flux produced in the core of the transformer. So this bidirectional flux is linked with the primary as well as secondary winding, and because of this flux we have an EMF induced in the secondary winding, which we take at the output, and we connect a load across the secondary of the transformer. However, the difference is that in transformer, it is a static device. It does not have any rotating or moving part. But a three-phase induction motor is a dynamic machine which has a rotating part. It is an electromechanical energy conversion device, right? So the purpose of today's lecture is to understand how this uh, motor rotates. Okay, so one thing we have already understood, that we have the conductors on the rotor, we have a rotating flux. This rotating flux cuts the conductor of the rotor, and because of this we have an EMF induced on the conductor, and then we have the rotation. So we will continue this point after few slides. So as of now, hold it here. Right, now let us come to the point. Now, a three-phase induction motor works on the principle of mutual induction. It is similar to that of a transformer, right? In transformer, as I have already discussed, we have a primary winding, then we have a secondary winding, right? So we give supply to the primary winding, and then we connect some load across the secondary winding, right? Fine. So we have the flux which is linking these two windings, right? So because of mutual induction, we have an EMF induced in the secondary winding, which is E2, and hence we have some current flowing in the secondary winding. We connect load across the secondary winding, but this is a static device. So transformer is a static device. That is, it does not have any moving part, as I have already discussed. Now, let us come to the concept of the three-phase induction motor rotation. The first thing is we have the rotating flux, right? We have a rotating flux. Conductors, this is one thing. The second thing is conductors are on the rotor, right? Rotor could be a cage rotor, or it could be a wound rotor, right? Rotating flux cuts the conductors placed on the rotor, right? So these 3 points, you can note down these 3 points and then we will discuss further. So up till here it is, I think, clear to all of you. Now let us come to, now for example, this is the stator and this is the rotor, right? This one is the rotor. Now we have the conductor on the rotor. So this is the conductor, right? Now we have a rotating magnetic field in the air gap. So this is the air gap, right? So we are understanding this concept by taking a portion of the three-phase induction motor. This is a symbolic representation, right? So just try to understand. We have a conductor which is placed on the rotor of a three-phase induction motor, and this is the flux which has rotating nature, right? Okay, so rotating flux it is, and its direction is clockwise, right? It is rotating in clockwise direction like this, for example. Now, now this conductor is stationary, is stationary. That means it is not moving at all. Now what? Now the principle of an electric motor is that when a current carrying conductor is placed in the magnetic field, the conductors or the conductor experiences a force, right? And the direction of this force is given by Fleming's left hand rule. So this rule is used to find out the direction. Now in three-phase induction motor, we do not give the current to the rotor. We do not give the current to the rotor. Then how do we get the rotation? This is the question. What is that factor which makes the rotor of a three-phase induction motor to rotate? Now, when we are not giving, or when the current is not given to the rotor conductors of a three-phase induction motor, then how are we getting the rotations of the rotor? This is the question. How are we getting this rotation? Now we are not providing any current to the conductors, and as far as a motor action is concerned, motor action is only obtained or achieved when we give some current to the rotor and so current to some the conductor, and conductors are placed in the magnetic field. Now we have a conductor, it is placed in magnetic field, we have a rotating magnetic field, but this conductor is not given any current. Then how are we getting the rotation? The answer is that no, this conductor is stationary initially, and the answer to this is that when this rotating magnetic field cuts this conductor, right? when this rotating magnetic field cuts the conductor, because this conductor is connected back to back with the another conductor which is its counterpart. So as per Faraday's law of electromagnetic induction, we have the EMF induced in this conductor, and then because this conductor is connected to the another conductor and we have a closed path here, so current will start flowing. So let us understand this thing. Now, because the rotating magnetic field is in this particular direction clockwise, so with respect to this clockwise direction of the rotating magnetic field, the direction of or the motion of the conductor will be anti-clockwise. So this conductor is moving in anti-clockwise direction, right? So if the direction of this conductor is anti-clockwise, direction of flux is downward. So Faraday said that we must have a conductor plus magnetic field and relative motion between these two. There should be a relative motion between these two. Now, in case of DC motor, DC machine, field is static, but conductors move, right? In case of transformer, conductors are static, but field is bidirectional, that is AC. Now, in case of a three-phase induction motor, we have a static conductor, but the field is rotating in nature. Now, this rotating field will cut this static conductor. The direction of this static conductor with respect to the rotating magnetic field is anti-clockwise. So this is clockwise and conductor anti-clockwise. But but it is not yet moving. It is not yet moving at all. Now, as soon as this magnetic field will cut the static conductor, the direction of its motion with respect to the field is given as anti-clockwise. This is the direction of magnetic flux. You can see here the direction of magnetic flux is like this. So as per Fleming's right hand rule, the direction of, because this rotating magnetic field when will cut this conductor and EMF will induce in this conductor, and the direction of that EMF will be given by Fleming's right hand rule, right? The direction will be outward, right? It is outward, right? And outward direction of a EMF or current will is always shown like a dots and circle. So this is the cross sectional view of conductor. So the current is outward. Current is outward, right? If we have a cross, then this is current is inward, right? Current is inward. It is going into the conductor, and here it is coming out of the conductor, so the current is outward, right? I repeat, the rotating magnetic field cuts the stationary conductor. The conductors are connected back to back. They are shorted using end rings. So this EMF which is induced in this conductor will generate some current to flow in the conductors, and the direction of this EMF and the current is given by Fleming's right hand rule. Now, as soon as we have the current in this conductor, because of this rotating magnetic field which cuts this conductor, we have a current carrying conductor placed in the magnetic field, right? So you can see here this conductor now has some current, right? And we have the magnetic field here, so we have a current carrying conductor placed in magnetic field. Hence this conductor will experience a force, and the direction of the force on this conductor is given by Fleming's left hand rule. So Fleming's left hand rule is used to find out the direction of this force, right? Now the direction of this current is given by Fleming's left hand rule, right? So now you can see here the direction of flux is downward, the current is outward, and the direction of motion will be in this particular. So that means as soon as this conductor has some current induced in it because of Faraday's law of electromagnetic induction, it is now current carrying conductor placed in magnetic field, and hence it will experience a force, and the direction will be given by Fleming's left hand rule. Now this conductor will start rotating, or this rotor, because the conductors are placed on the rotor periphery, there are n number of conductors placed, so all the conductor will have the same direction, and hence this conductor will start rotating along with the direction of the magnetic field, right? So because the rotation of this rotor is achieved due to the induction of the EMF in the rotor conductors, and hence this machine is known as induction motor, right? Now why do we call it as asynchronous motor? The reason is that asynchronous because the speed of the rotor is always less than the speed of the magnetic field, where nr is the speed of rotor and ns is the speed of rotating flux, right? So this is how we get the rotation of the three-phase induction motor. And since this rotation has been achieved because of the induction principle or mutual induction, so this motor is a self-starting motor. As soon as the three-phase flux, the rotating flux is developed in the air gap, it starts cutting the stationary conductors placed on the rotor. The conductors are connected, shorted using end rings. So because of this EMF, the current will flow in these conductors, and now we have the current carrying conductor in the magnetic field, and hence we get the rotation of the rotor, right? Now let us come to, you can see this one. So This is the cross sectional, the front view of the cage rotor. So this is the front view of cage rotor, right? Now this cage rotor is basically, now when you have the magnetic field rotating around this cage rotor, so this magnetic field will cut these conductors, right? And these conductors you can see are connected, are shorted to one another through these end rings, right? These are the end rings, or the made up of the aluminum or copper, right? So these are the end ring you can see here, right? So now when emf is there, which is given by minus d phi by dt, right? So this conductor is connected to some its counterpart. So like this conductor is connected to here, this conductor might be connected with this one, this conductor is connected with this one. So these conductors will have the current flowing in them, right? These conductor will have some current flowing in them like this. So when we have current flowing in the conductor bars, so we have current carrying conductor placed in the magnetic field. So let us say this is the magnetic field, and we have the motor action. So this is how the three phase induction motor starts rotating. Now you can better understand from this particular pictorial diagram. We have this is the rotor, which is a cage type formation, right? So these are the conductor bar, these are the end rings. It is placed in the stator will have some, there will be some three rotating flux in the air gap. This flux will cut these conductors and we get the rotation. So here we have an animation, right? So this is how you can see it is rotating in clockwise direction. So we have the conductors, these conductors are on the rotor periphery, and we have a three phase flux which is cutting these conductors, and hence we have the rotation of this rotor, and that is why it is called as self starting motor. So now this is how this particular motor works. So now there are two things you need to understand. Ns is the speed of rotating flux, and nr is the speed of rotor. So to have the motor action in a three phase induction motor, nr always is less than ns, right? And the difference of nr or ns minus nr is known as slip. So this is required to have the motor action, right? So if ns is equal to nr, or you can say nr is equal to ns, then the relative motion between flux and conductor is zero. Hence, no d phi by dt, so no emf and no motor action. That means we cannot have both speeds same. Now here the interesting thing is that you can see in this particular diagram, the interesting thing is that the field, flux and conductors both are moving, both are in motion, both are in motion, but at different speeds, right? But at different, this is the necessary condition, otherwise we will not have any induction. Okay, so to have this motor action in case of three phase induction motor, the condition is that the there should be a slip, and slip should not be zero. Slip should not be zero, right? And R should be less than ns. This is the condition, otherwise there will not be any motor action, because the relative velocity means both the flux as well as the conductor will rotate in the same direction. They are rotating in the same direction, right? uh, Field and conductors are rotating in same direction with the different velocities, right? So if they have the same velocity, their direction is also same, so the relative movement between the two will be zero, and hence zero means there is no d phi by dt, and there is no d phi by dt, there is no emf, and there is no emf, there is no current, no current carrying conductor in the magnetic field, and hence there is no motor action, right? So this is very very important to have the slip or the difference between the two speeds to have the motor action. So in this lecture we have understood that a three phase induction motor works on the principle of mutual induction, on the principle of mutual induction, right? So this was all about today's lecture. Thank you so much.